Hello and welcome to Toddcast number two. Uh, Hopefully the first one went, I don't know, just fairly straightforward. This one's going to be kind of the same topic, but now I'm going to be a little more detailed and a little more complex in the structures we look at. But what we looked at the first time, we did the HONC rule, hydrogen making one, oxygen making two, nitrogen making three, and carbon making four bonds in stable structures. And those structures are referred to as Lewis structures. Lewis structures do not show any three-dimensional accuracy. They're not meant to do anything other than show the connectivity of the molecule. And so want to just revisit the same set of things or same set of rules we had before. Carbon makes four bonds, one, two, three, four. We alluded towards the end of that video, the first podcast, that you could have a double bond or a triple bond. So two bonds of the same atom or three bonds of the same atom. And we'll get into that as we go. But four bonds total. Nitrogen is going to make three bonds and have a lone pair. Oxygen is going to make two bonds and have two lone pairs. And hydrogen is going to make one bond. So Lewis structures, they just simply show the connectivity of the atoms within a molecule and the electron pairs. But again, just want to emphasize, they do not give you any accurate information, any precision into where the atoms are physically located. So let's say we have a molecule like this. So let me just double check the connectivity. Going to start with carbon, 4, 1, 2, 3, 4. As mentioned, it has a double bond. So two of the bonds are to oxygen, but it has 1, 2, 3, 4 bonds. So that's fulfilled. Nitrogen is not in there. Oxygen has 1, 2 bonds and two lone pairs. And hydrogen, there's two hydrogens, they each have one bond. HONC rule satisfied. So this structure is a valid structure. This molecule is known as formaldehyde. So I'd like to give some of the terminology early on. We're not responsible for it yet, but the more you hear it in early on, the easier it's going to be when we actually review it later on. This molecule over here, NH3, is known as ammonia. You'll probably learn these molecules in passing, but we're going to go into more detail about them in this class than we did in previous classes. But ammonia, nitrogen with three hydrogens. So let me just do the same checklist as before. I have no carbons. I have one nitrogen, has a lone pair. Check. And 1, 2, 3 bonds, check. There's no oxygen, and their hydrogens make one bond, 1, 2, 3 hydrogens. Structure works. Okay, so let's see how we did on a bigger molecule. So I promised we'd do a little bit more complex molecules. So let's see if I've done my job right. So carbon, 4. This carbon makes 1, 2, 3, 4. That's good. This carbon here, 1, 2, 3, 4. That's good. This carbon, 1, 2, 3, 4. That's good. But this carbon, 1, 2, 3, 4, 5. So that one, I messed up. Okay, I'll fix it eventually, I hope. Hydrogen, well, oxygen I should do next. Excuse me, there's no nitrogen to worry about. Oxygen has two lone pairs, so there's an oxygen, two lines, lone pairs. So from oxygen's perspective, it's got two lone pairs, two bonds, so it's good. And then hydrogens make 1, 1, 1, 1, 1, 1, 1, 1, 1. So hydrogen is no problem. But for carbon, it ends up, and this is going to be kind of a cool little trick, because carbon makes an even number of bonds, and oxygen makes an even number of bonds. If you have molecules with just carbon and hydrogen, or carbon, hydrogen, and oxygen, you must always have an even number of hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9 doesn't work. So I have one hydrogen too many. So I'm going to get rid of that one right there. So if I go through this, I should clear this up. That bond right there should go away. Now, 4 bonds, 4 bonds, 4 bonds, and this one, 1, 2, 3, 4. So we're set. Okay, this compound is known as butanone. So but, 1, 2, 3, 4. So one carbon is called meth, two carbons called F, three carbons called prop, and when you have 4 carbons in a row, it's called but. And then this is known as a ketone. Again, we'll get into the nomenclature as we run into these molecules, but it's never too early to get a jump on it. So butanone. And then we'll throw one more. So let me just go through the same thing we did before. Carbon 1, 2, 3, 4. Carbon 1, 2, 3, 4. So carbon set. Nitrogen 1, 2, 3, 4. Uh-oh. So that one's off. No oxygen. And then all the hydrogens are 1, 1, 1, 1, 1, 1, 1. We're set. But nitrogen should have 3 bonds in a lone pair, not 4 bonds. So based on that, this nitrogen has 1, 2, 3, 4 bonds, one too many. So I'm going to get rid of this. Now, here's that same trick, but flipped around. So when it was just carbon, hydrogen, and oxygen, even number of hydrogens, because nitrogen makes an odd number of bonds to make it work out, you must have an odd number of hydrogens if you have an odd number of nitrogens. So 1 is an odd number. So it should have 1, 2, 3, 4, 5, 6, 7, 8. That's one too many. So I need to get rid of one of these H's. So now we have 4 bonds with carbon, 4 bonds with carbon, nitrogen, 3 bonds, and a lone pair. We fit what we want. So the HONC rule, very important you follow it. HONC rule gives you valid Lewis structures. So we really are doing the same thing we did in the first Toddcast, but now little bigger molecules. Molecules are going to get significantly bigger. So 2 carbons and a nitrogen, 4 carbons and an oxygen, a little bigger than what we have been doing, but we're going to deal with molecules that have 20, 30, 40 carbons at times. So knowing how the connectivity works, absolutely essential. Okay, so I want to consider different Lewis structures. So again, this is what we did in the first Toddcast, where we had carbon with 1, 2, 3, and then a 4th bond to O, so 3 H's. H's are all 1 bonds, carbon has 4. Oxygen 2 bonds with 2 lone pairs, and H single bond, so we're set. Ammonia, we just did the one on the previous slide, lone pair and 3 bonds to H. Sulfur, mentioned the first time we did it, had a compound called a thiol. And again, we'll get nomenclature as we go, but in the thiol, sulfur had a S with just 2 bonds like oxygen. But as mentioned, because it is in the 3rd period of the periodic table, it can have an expanded octet, so it can potentially make a 5th and even a 6th bond. So here is sulfur making 1, 2, 3, 4, 5, 6. So the octet rule doesn't hold with sulfur. It sometimes can fit, but it's not an absolute. So we don't call it the octet rule for that row. But let me make sure everything else is set. So sulfur making 6 bonds, we live with it. Oxygen makes 2 with 2 lone pairs. Oxygen 2 lone pairs and 2 bonds. Oxygen 2 lone pairs and 2 bonds. Oxygen 2 lone pairs, 2 bonds. H's with 1 bond each, so it works. Here's where Lewis structures get a little bit interesting. So we use them to represent molecules in shorthand. Mention they're not structurally accurate. They don't take into account 3-dimensional shape, but they also are not always perfect. So oxygen, if you think about our atmosphere, about 3/4 is nitrogen, a little more than 3/4 nitrogen, a little bit less than a quarter is oxygen. Nitrogen is completely inert. If you had just nitrogen in the atmosphere, we would all die. It's unreactive, not going to help us out. So that's good in some ways, it helps preserve things. So you put things in a nitrogen environment, they will last for a long time. But oxygen, highly reactive, and that is because it actually doesn't quite do that. The reality is oxygen is a very weird molecule that actually, if you look at the energetics of it, we can think of it more precisely, more accurately as a single bond, 2 lone pairs, and then what we call a free radical, single electrons on each atom. So I toss this not as an example that I want to test yet, but this is one of those secret of life perspectives. So because it has an incomplete octet, technically speaking, it becomes highly reactive, and therefore we can burn things. So O2 is such a highly reactive molecule, it can react with some of the most stable hydrocarbons like methane, ethane, and give you a lot of energy. So this biradical, as it's called, has a single electron here and here, doesn't actually make that second bond. It wants to form a second bond with some other element. So consequently, it is highly reactive. It wants to go form some bond somewhere. And so oxygen, we use it to break things down. We use it in a process known as oxidation. We will cover that so thoroughly this semester that it'll be old news soon. But oxygen, one of the exceptions to the rule. So I want you to hang on to this visual for when we get into oxidation later on in the semester. Okay, so let's see if we can recognize things. Your job, quickly recognize the rules. So HONC, honk, 1, 2, 3, 4. Does hydrogen make one bond? Yes, yes, yes. And CH3, you're going to assume it just means the H's, the three H's on carbon are all single bonds. So this is, again, a shorthand. There are no oxygens, no nitrogens. And then carbon makes 1, 2, 3, 4 bonds because of double bond. 1, 2, 3, 4 bonds because of double bond. Everything fits. It's a good structure. So all carbons have 4 bonds. All H's have 1 bond. Good structure. Okay. This structure over here. Hydrogen 1 bond, 1 bond, 1 bond. Carbon has 2 bonds there, so 2 H's makes sense. This carbon 1, 2, 3, 4. But this carbon right here, 1, 2, 3, 4, 5 bonds. So carbon must have 4, but it actually makes a 5th. So this red carbon right here is inaccurate. So that would be a bad structure. That is incorrect. Can't do that. So recognizing wrong structures may seem like a weird thing to do, but when you're drawing out reactions, you have to show accurate bond connectivity. So chemical reactions involve the making, breaking of bonds. So if you have the wrong bonds, that molecule won't exist, and that reaction, as you indicated, won't be valid. So no, you have to have valid structures to indicate a valid reaction. So if somebody drew that structure, they would not get credit. Okay, so we'll do another one. In this case, everything has just carbon and hydrogen. This molecule, everything is then going to be 4 bonds like carbon, or 1 bond like H. So in this case, 3 H's on a carbon, check. This carbon has 3 bonds to H and the 1 bond to carbon, so 4 bonds, check. Carbon 1 and 3, so 4. This carbon 3 and 1, so 4. Carbon connected to a carbon, the way I've drawn it. So if I were to draw this out more precisely, it would look like this, with 1, 2, 3 bonds to H. 1, 2 bonds to H, so we call it a CH2. 1, 2 bonds to H, call it a CH2. And then 1, 2, 3 bonds to H, call it a CH3. Okay, so 4 bonds, check. 4 bonds, 4 bonds, 4 bonds, 4 bonds, and 4 bonds, everything's set. All the hydrogens have 1 bond. So that structure, that is valid. So all the carbons have 4 bonds, all the hydrogens have 1, good structure. So I'm gonna have the same structure, but now I'm gonna have a little bit different over here. So again, I want to draw my connectivity out more thoroughly. So that would be the O, CH3, C with 3 H's, C with 2 H's connected to a C with 3 H's. So if I look at this, the things that I've messed up, so messed up this, now I'm going to be complete. 4 bonds to carbon, check. 4 bonds of carbon, 4 bonds of carbon, just like it was here. That part's valid. 4 bonds of carbon, 4 bonds of carbon, 4 bonds of carbon, but oxygen has 3 bonds, which means it would only have room for 1 last lone pair. So this one is out because carbon is fine, hydrogen is fine, but oxygen has 3 bonds. Can't happen, so therefore, bad structure. The structure over here, H has 1 bond, again, C with 3 H's. So I'm just gonna draw the H's in this way. And then same thing here, you're gonna, this lower one, CH3 is 3 H's. So nitrogen has 1, 2, 3 bonds. Hydrogen's all have 1. Carbon has 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Perfect. Carbon has 4 bonds. Hydrogens have 1. All nitrogens have 3. The one thing I'm missing, and hopefully you're sitting there yelling at your computer, lone pair, have to have a lone pair of nitrogen. Now it is complete and good drawing. And then finally for this one, CH3, 3 H's, so like that, CH3 set, one bond there, one bond there. So carbon 3 H's in a bond, so 4 bonds, 3 H's in a bond, 4 bonds. H and H are fine, carbon 1, 2, 3, 4. But that nitrogen right there has 4 bonds, one bond too many. Okay, foreshadowing. For now, I'm going to call it a bad structure, but if I put a plus charge on it, so food for thought, that means it is a viable cation structure, just saying not a neutral structure. So I want to get a little ahead of myself, but just if you see that in the future. So you should recognize something is weird here. I'm going to call it a bad structure for now. We have to fix it and figure out what's going on. Okay, so not too bad. So the first two Toddcasts, I'm hopeful, are fairly, I don't know, straightforward and just we're drawing lines, connecting things. Again, this only comes with practice. So that's what this is all about. Once we're up to full speed, this has become second nature. So try to get involved in it early on. And I will see you at the next podcast. So going to sign off on this one. So far, so good. 2 down. See you soon. Bye.